In this class, we'll look at how we use Markov chain Monte Carlo to solve a regression problem with real data. All right, the problem we'll look at is predicting SAT performance, and we have data from all 50 states, and we will look at how the students perform on the SAT in those states. This comes from a paper by Gruber in 1999, where he showed that SAT performance actually decreases with increasing high school spending. So if you look at the plot, you can see this. And this, in fact, is an example of Simpson's paradox. As Gruber points out, some people latch onto this and try and indicate that school spending is not related to performance. But in fact, it's a real good example of Simpson's paradox in that we're missing a variable here, and that's the percent of students who take the SAT. Because in states where large numbers of students take the SAT, they tend to be states that have higher educational expenditures, whereas, and with larger numbers of students taking the test, their scores on average are lower, whereas in states that have few students taking the test, these are the only ones who are competing to go on to college at the schools that require the SAT, and their scores tend to be higher. We can look at this problem as a Bayesian multiple regression problem. And let's start at the bottom of this Kruska diagram, which is a convenient way to look at it. We're going to model the likelihood here as a t-distribution. And recall that we have three parameters in the t. The new parameter is the degrees of freedom, the mu is the location, and the sigma is the scale. So the new parameter then, we're going to model the prior with an exponential because the degrees of freedom have to be strictly positive. The mu parameter, the mean or the location of the student t-distribution, we're going to model, of course, with the regression equation. And the regression equation has three parameters in it. It has the intercept term, beta naught, and it has the two beta parameters, one for expenditures and one for percent takers. And each of these we're going to model with a Gaussian, and we're showing it as a different Gaussian for the intercept, but in fact we're going to model all three with the same Gaussian, centered at 0 and with a common standard deviation. The scale parameter in the t-distribution, again, it has to be strictly positive, but in this case we'll model it with a uniform. So let's now look at the Python code for this problem. So this is the Jupyter notebook that contains the code for this particular problem. And most of it comes from the Git repository provided by Jody Varmanhoven. And the link to that page is there. There's quite a bit more than we have here. And I encourage you to take a look at it because you can learn a lot from what's provided there. All right, so we start by loading the packages that we normally use for Python. We also set a little bit of style definition. Then we load the data. The data are available on Colab, and you should download the data and obviously use your own path for where you've downloaded the data to. And you can see what the data look like. We have a combination of class labels in the state, floating point numbers with spending and the like and salary, and integers as well, including the SAT scores. Okay, and then the data itself, when we look at what they look like in the table, you can see the state, spending, student-teacher ratio, salary, percentage who take it, and then the scores on the SAT, verbal math, and then total score. So that we define the data matrix X with two predictors, spending and percent takers. We defined our response variable as the total SAT scores. We mean and standard deviation scale both the predictors and the response, which means we subtract the mean and divide by the standard deviation. And then we've got a plot here. So this is showing you the plot using GraphViz that's automatically generated. And you can see we have, as we talked about, the exponential for the degrees of freedom as the prior for the degrees of freedom, the gamma as the prior for the scale parameter in the t-distribution, and then the Gaussians for the beta parameters in the regression model. Another version of that is provided by the Kruska graph, and that's shown here. We've just brought it, and we've already talked about it. This is putting it in our Jupyter notebook, so we have it available to us when we need it, and we can go back and refer to it in terms of describing our model. Then we set up the model with PyMC3. This is just defining what we specifically defining our prior distributions, the Gaussians, defining the regression equation, defining the exponential for the degrees of freedom, the uniform for the scaling parameter, and then setting the likelihood as a student t distribution with the variables described. Okay, then we actually release the MCMC code to run. In this case, we tell it to run 10,000 times. I used 8 cores on my machine to run 8 different chains at the same time. And the target acceptance we set at 0.95. You can see the results in the trace plots and the density plots, and they look very nice. There are actually 8 plots on top of each other in each case. So, for example, the beta naught is the intercept term, and you can see its density is shown there, nicely distributed around 0. You can see the results for the trace plot, again, looking very nice, not showing any problems on convergence. Same is true for the other 2 betas for the 2 regression variables, expense and percent takers. Both of them look very good. The same is also true for the gamma distribution that we have on the degrees of freedom. Now this one is skewed, so we're seeing the skew there, but again, we expect the skew to be in this gamma, and it in fact is there, and it's behaving nicely as we would like it to. And finally, the uniform distribution is actually looking more like a Gaussian in its search, which is fine, and again showing good convergence. We transform, this code just transforms those results back to our original scales so that we can actually say what the results mean in terms of the original scales for these variables. So you can see that the intercept looks pretty good. It looks like the intercept is right around 1,000, somewhere around 999 or 991 for the mode of that. The 95% HPD is 95% high posterior density. This is effectively a confidence interval in a Bayesian sense. And for the intercept, it goes between about 948 and 1,035. The important things, though, are spending and percent takers. And notice that in spending, the mode is 12.6. So in fact, spending is a contributor to performance on the SAT. So in other words, the performance of the students in that state. And you can see it's a factor of better than 12. With the HPD, high posterior density region, between 4 and 21. So that's telling you that spending is in fact a major contributor to performance by the students on the SATs. You can see also that percent takers works exactly the opposite. It's a minus almost 3, minus 2.8. So as the percent takers goes up, the average performance on the SAT goes down. Again, exactly what we'd expect. More students in the state are taking the SAT, which means that the average is going down. States that have only a few students or fewer students take it are those students who want to apply for colleges that require the SATs. Okay, and the other results are showing you the results for the parameters of the t-distribution, the scale parameter, and the normality parameter. The normality parameter is basically the degrees of freedom parameter. We've just taken log base 10 of the degrees of freedom parameter. This is suggesting that the likelihood is in fact well modeled by a Gaussian, but we didn't know that going in, so using the t-distribution made some sense. Okay, and the last thing we've done here is we've done plots of each one of the components of this particular problem so we can see the relationship. And in fact, you can see that spending and intercept are correlated with each other. percent takers and spending are slightly correlated with each other, and the other components are not correlated. So this gives us a sense of how our model is performing. The correlation between spending and percent takers suggests that we may want to use our additional results from Bayesian regression, which effectively takes us to a ridge regression approach. So this example gives you some code that shows how MCMC works for Bayesian regression.